think I can still wait a few minutes for people to arrive.
Yeah, sure.
Let's, okay, so I think I will start now.
Okay.
If someone can tell me if everything is okay, if you can hear me.
Yes, sir. Yes,
okay.
Yes.
Thanks. So, so good. I think good evening for people in India. I will talk about experimental studies in stratified flows, mixing waves. So, just my name is Sylvain Joubeau. I will do my lecture on Keynote, and I will show many movies during these two lectures. So I'm mostly an experimentalist who worked on different topics related to geophysical flows, stratified flows, rotating flows, multi-phase flows. I want to talk about experiments. It's very important to do experiments in such topics. They are complementary to numerical simulations and theory, and it's this discussion between people who do numerical simulation, people who do experiments, help for the understanding on everything stratified. So I will show movies, try to interpret them, make some calculation around this movie. But before going to the details, I will recall two things. So for stratified flows, the density depends on the position and mainly depends on Z. You had 3 lectures already, so you may know many things I will discuss just in the introduction. And you have different variables that are interesting in stratified flows. That's the velocity, V, the pressure, P, and the density. Oh. There are many other things, but that's 3 very important. Quantities, and an important question for experiments, it's how can we measure these quantities? These quantities. I will just go a bit more in details on the density Rho, basically we have two important properties. It depends both on the salinity, so we use variation of Rho due to salt, and the other one is due to temperature. And so basically you have an equation on the first order, which is this one minus beta S minus SA minus beta T, T minus TA. Basically, SA and TA are quantities that reference quantities, and you have a dependence on the density with salinity and temperature. And that's what will be used in experiments. Just to go, that's the density versus temperature. I will just put it in the here. Sorry. Anything that I already. Okay, so what I have here is density versus the temperature. You can see that the density decreases with temperature except near 0 degrees. So that's beta T negative, positive, sorry. And you can do the same with salinity on the typical, with this one. And with salinity, you increase the more salt you add to your system, the denser the fluid is. That's the second one that is interesting. Negative. And basically, we will use these two characteristics of properties of the fluids and basically on water to do experiments. That's two first results. The first experiments I want to discuss will deal with non-continuous stratified flow, but two layers fluids, and it's something that is called lock exchange experiments. I think basically what you want to see, you start with a system that is like this, a tank. In the tank, you have two sides. On the first side, you have a fluid that is at density of 0. We will assume the same temperature, T0, and here, no salt. On the other side, you have a density which is 1, same temperature, but SA positive. So the fluid on the left is denser than the fluid on the right. And the experimental system I want to discuss that we remove this bar. So if we do that, you can see this experiment, which is called a gravity cube. This is a movie that you can find. It's from Australian National University. And I added some dye. I did some dye on the left part to see the motion of the system. So you smoothly remove the barrier, and as expected, the denser fluid go to the bottom of the container, and the light fluid is above. You can see that you have a current that is going at a constant, at at a velocity. And one question is that, can we measure this velocity? And the dependence on this velocity with the parameters of the two fluids. And this is called gravity current. At the end of the system, what you observe is that you have two layers of fluids, one which is below, which is at density ρ1, and one on top at density ρ0. If you look carefully, sorry, we have this. If I do this movie again, if you look carefully, you can see here some wave breaking here, which induce mixing. So between the two layers, there are a mixed fluid that is mixed, and it's continuously going from ρ1 to ρ0 at the interface. And it is just because of this small mixing, overturning events on some mixing. And I will come back later in my talk to study this properly. Clearly, what you can obtain in this movie using this backlight, you can separate the interface between the two fluids, and you will look at the behavior of the interface. If I come back here, so what you have is something that can be schematically sketched like that. You have a velocity here and a velocity here, v1, v1. And okay, so what you want to do now is, could we study sorry, could we predict the velocity v1? That's a classical example in fluid mechanics to predict this velocity. I will do it by first showing some movies. So what we expect is that ρ1 is larger than ρ0. The larger ρ1 is, the larger the velocity will be. So we expect that v1 is a function of delta ρ, which means delta ρ is ρ1 minus ρ0, and v1 is larger if delta ρ is larger. So could we see this experimentally? So to see that experimentally, I go back to this movie and I will do another one. In this movie, we have three systems, and ρ1 is different because the density, the concentration of salt is different. At the bottom one, the concentration of salt is much larger than in the top one, which confirms that the velocity is much larger if delta ρ is larger. You can still see the breaking that induced some mixing. Then you have the rebound on the wall on the right, and you come. And the question is that in this movie, what you can also see, I will come back to that, you double, you multiply by 2 for the middle one, you multiply by 3 for the third one. It seems that it's not proportional. So we will try to understand this. So a movie with 3 concentration of salt. Concentrations of salt. Then that's a part where I want to try to understand could we estimate the gravity, current, speed. And I will just start with a very short dimensional analysis of this problem. So in this problem, we have for parameters delta rho, which is 1 minus rho 0. You have the gravity, which means that the denser is going below, and you have the height h of the system. You have some other lengths, but the one that matters is h. If you do a dimensionless number, and I forgot one, you have another one, which is u, the velocity. H is the height of the system, and g is the gravity. It's easy using this 4 quantity to write a dimensionless number. And this number is u squared delta rho divided by rho is not g h. You have the velocity, and to have from the 3 first parameters a velocity, which is this one, and this is equal to a number squared f, which is the food number. This is a very important number when you study buoyancy-driven flow, which is the case, for example, for stratified flows. So that's the first things we want to see, that we have a very simple expression for the velocity of the current as a function of this number, of the full number. I will go a bit further in this analysis, and I will do a quantitative comparison. To do that, I will use an experimental study that has been done in Cambridge, in UK, by in the group of Paul Linden and Stuart Dalzell. And it was a study written in GFM in 2004. And I will just copy this one. Yeah. Okay. So in this one, what you can see is that you track the position of the interface as a function of time. The time has been rescaled by a time scale given by this formula, and this time scale is g prime over h. G prime, g prime, it's the reduced gravity and is always given by the density difference divided by the mean density. Basically, the density is close to ρ1 or ρ1 or ρ0 are usually close, doesn't really matter, and g. That's the reduced gravity. You can define a critical time scale, which is h over g prime, the square root of h over g prime, and the time scale is rescaled. T divided by T star. And here is the position x divided by h. X is this position. And if you look at these results, what you can see, the black dotted or the position of this interface, the dotted that are in white is this one. So both have the same behavior, and they have a linear behavior. Draw a line, a straight line like that, meaning that x over h is proportional to t over t star. And if you look at the slope, you find a slope 1/2. And if you rewrite the quantity, x over t is u, and you can write the one you have u is 1/2 the square root of delta rho over rho g h, which is a quantity that is given by the full number is 1/2. Meaning that knowing the full number, you know at which velocity the gravity current will go. And that's a result that is taken from the experiments. And what I want to explain now is just basics features to derive such results. And this is an kind of very easy calculation. So I will not go into all the details of the derivation. I will just give you the equations we have to write to obtain the theoretical result, which will give you this coefficient 1/2. Basically, it's a theory made by, make a reference, 1968. That's 50 years ago. The system you are considering is this one. And you look at this behavior, and this you make change of the frame of reference. This fluid is at rest, which is the fluid ρ1 over a small h. The distance between the two plates, between the bottom and the top, is large h. This fluid is going at velocity u, and here at a velocity u1. And just I will add 4 coordinates. This is the point which is called O. Sorry. This is D, B, C, D, and this is E. I forgot one dimension. This is 0. And to make the analysis, this is a very classical problem in fluid mechanics. You will use conservation. You will use first mass conservation. Mass conservation, it's an easy equation. UH equal U1 large H minus small h. The second one is the conservation of momentum of the horizontal flux. This will give you another equations for the system. I will not derive this equation. And you, to do all this problem, you will need to use the Bernoulli equation on two different lines. And for example, at the bottom and at the top. And basically you have with this you have 4 equations, you have 4 unknowns, which are small h. You don't know what the thickness is. You have u1, you have, of course, you have 5, 4 unknowns. You have the velocity u, and you have the velocity, the difference of pressure delta p, which is p at the pressure in B minus the pressure in C. And by doing some analytical calculation, I will not derive everything. Is not the goal of my talk. We obtain h equal 0, or h does not really a sense, so we don't care about this one. And the second one is h over 2. And since with this small h, you will get also the results for the full number, which is u over the square root of g prime h, which is equal to 1/2. So that's a very classical calculation you can do. And I have shown you the experimental results, which will give you a slope of 1/2. The theory gives you a full number of 1/2. You have an excellent agreement with experimental results. Of course, this is not always the case. Viscosity can matter. If you have large density difference, it can also change things. But in simple system with salt, you have this kind of behavior. So that's a very simple system, and you can calculate completely the gravity current, and you have something simple. Just to show you what happened next, you can do the same experiments and start with a 3-layer stratification. You have an intermediate density, and the intermediate density will go like as a gravity current between the 2 first layers we have created before. And now, at the end of the system, you have a 3-layer stratifications. It's also simple experiments you can see here. Dense fluid, less dense fluid, and even less dense fluid. So just 3 layers stratification. By this experiment, you have you have this system. You have one at density O2, O1, which is smaller than O2, and node that's smaller than ρ1. And that's a discrete stratification. Of course, in between, you have a small width to go from one density to the other one. One thing we are really interested in is to go to not a discrete stratification, but continuous stratification. You had the talk this morning about internal gravity waves, and usually the study is with linear stratification or nonlinear stratification may happen sometimes, but continuous stratification. And this is something I want to explain to you how we do that in the lab in a controlled way. Formation of a stable stratification. So the last one. If you have any questions, don't hesitate to put them in the chat, and I will answer any question you have. Or if you have any questions up to now. Okay. So the first, in the previous section, I have explained what happens in two fluids in the log exchange experiment. We do something similar to work with a continuous stratification, but in a continuous way. So ρ2 will be very close to ρ1, and we each time we will add a small gravity current at a density which is close to the previous one, and we will create stratification, but the density increases continuously with depth. And my goal is to explain how can we obtain a stratification in which ρ density increases slowly with depth. So it's in experiments we do this every week, almost sometimes every day. We decide which stratification we want, and we have a way to create exactly the stratification we want. Formation of the stratification. We want. And that's the first studies, and I will show you two studies. The first one is what we use in our lab, which is the double bucket method technique. Okay. This technique works with temperature or salinity. In the lab, we always use salinity. And I will show you after another experiments in which you have a stratification, but with temperature. I will just add some reference on this technique. So long time ago, 1960s, you had Oster and Moto in 1963. And their method was generalized by Hill in 2002. With this generalization, you can have any stratification or any tank shape. Okay. So just to show, I will make a small sketch of the experimental system. It's called double bucket for a reason. So you start with a tank. The first one, you have a first tank at a density OS, water. This tank is, you have fluid is going from the first one to a second tank. The water. Here you have something to mix continuously the fluid, so you have a homogeneous fluid at a density rho m that depends on time t, with a volume Vm time t. And then from this tank, you go to, what is interesting is the experimental tank. So I will show you a stratification we realized in the lab, and I will then answer to your question about the diffusivity of salt, but it's a very good question. So you have the height here and the density in the tank, ρt, which depends on its altitude, it depends on t. Easy. And basically what you have here, you go to a flow rate, that is Q1, and here we are taking fluid from the other side to a second flow rate, Q2. And so I will present the case where you have Q1 or Q2. You can do also experiments where you just have one pump at Q2, and you can use communicating vessels, but it will give similar stratification. It's what we use for linear stratification. So what I want to explain is how we get to the we want to have the evolution of rho in the tank as a function of z. That's the question I addressed in this system. So basically the density that is arriving in the tank at T is the density taken from the tank where the fluid is mixed, the middle tank. Then first, the altitude Z is obtained by saying that the integral between say 1 to 0 and t of the flow rate Q2, Q1, dt. Just a conservation of the volume, you have the flow rate, which increases the volume. Since Q2 can depend on t, you need this integral. And on the other side, that's the area of the tank at an altitude Z1. If you do that, that's the general formula. I will do two simplifications to explain why we can get the stratification. Then I will come back to this later. So A is a constant, A naught, and the same for the flow rate. So if you do that, that's an easy calculation. The altitude, the height of the water at time t in the tank is given by 1 over A naught Q2 times t. That's the first thing. The second thing is, can we get the determination of OM of T? So the density in the tank in the middle. So to have this value, then we'll use mass conservation, which is d over dt and Vm. So the density is the density that's arriving in the tank minus the density out. That's mass conservation. And you have also volume conservation in the Vm over dt, which is volume that is arriving minus volume to going to the laboratory tank. I will not go into the detail of this derivation. Using the second one, you can simplify the first one, and you have this. The variation OM, which is equal to OS minus OM times V times, not V, Q1 divided by Vm naught plus integral 0 T Q1 minus Q2 T1. So for the bottom one, you integrate the volume conservation equation, and then you just arrange the different terms in the first equation. Using this equation, we don't really understand how we have the density as a function of the height. I will do some simplification for clarification, and then I will use the same. Q1 is a constant, Q2 is a constant, then if you do that, you have dt equal 4s minus 4m Q1 and not with Q1 times t. We'll answer the second question in the experiment. Q1 or Q2 are not controlled by the height of the water level, they are controlled by a peristaltic pump. You impose Q1, you impose Q2 in the peristaltic pump, and you have the flow rate you want during all the experimental realization. So with this equation, it's an equation that you can integrate. That's why I have this simplification of the constant for Q1, Q2, and that the area A is constant. Equation between 0 and T. So T is equal to S plus OM naught minus S 1 plus Q1 minus Q2 divided by Vn naught times T at power, which is Q1, Q2 minus Q1. That's just the integration of the previous equation. I'll just skip one step, and then by rearranging the different terms, you get this formula for the density in the tank. Since you had also Z, which is equal to 1 over A naught Q2 times T, you can get OM as a function of Z. So the density you had in the tank is a function of Z, which is equal to rho S, the density on one side, plus the initial density on the other side, 1 plus Q1 minus Q2 divided by Vn naught divided by Q2 times A naught Z Q1 divided by Q1 minus Q2. So in the general feature, you have such formula, and since you have seen that an easy stratification is a linear one, to do a linear stratification, sorry, it's Q2 minus Q1. A linear stratification is obtained if Q2 is 2 times Q is 2 times Q1. Basically, you want Q1 divided by Q2 minus Q1, which is 1. So you get this physics. So I come back in this system, the flow rate here is 2 times smaller than the flow rate here. And using this, you get a linear stratification, which can be written like Z naught minus OM naught divided by A Z to Vn naught. So knowing the shape of the experimental tank, knowing the density, the initial density in the two tanks used, two tank on the side that is used for filling the tank, and you need to know the initial height of this tank. you have the stratification you want, the linear stratification you want, which is given by this expression. So that's in theory. And this method is easy to implement experimentally. Realization easy to implement. Sometimes I say easy. PhD students who have tried to do it, usually one or two stratifications they tried are not very good, but it's not so difficult to see what are the problems we can have. I will show you an experimental realization, which is this one. It's also taken from this Australian National University movie. So the way they do the tank, the stratification, it's shown in this movie. You have something, a flotation device. So here what you do is you fill the tank by what's called the top. So you inject less and less dense fluid. The thing becomes lighter and lighter. That's why the fluid going at the surface at each time. You can do experimentally, we do the same by injecting at the bottom, and then you inject more and more dense fluid, and gravity current are at the bottom. I just want to show you one something particular in this movie, which is this here. What you can see here is that the image is kind of blurry. This is because you have some mixing between the fluid that is already present in the tank and the fluid that you are injecting from the flotation device. And you have this some mixing that is inside the tank. And that's one of the major issues in the experimental realization of the double bucket system, is that you want that this mixing is reduced as most as possible. You don't want this will alter, will have some effect on your stratification that will not be too good if this mixing is very large. So you have to design your device here so that the fluid is arriving very slowly into the tank, so you don't have really vertical motion that will induce some mixing. It means that the flow rate Q2 that you control with a peristaltic pump is as small as possible. And of course, experimentally, we don't want to fill a tank in many days. So we want to fill the tank in few hours. So you choose the flow rate Q2 that is large to have a filling that is not too long, but not too large not to have mixing. So it's just the first try when you have a new setup that will give you what is the good flow rate you need to use to have a nice stratification. So Q2 has to be small so that there is no mixing in the tank. That's important. And just to give you some idea, in a laboratory experiment that we have in Lyon, laboratory experiment, I will just give you some dimension. Uh, 17 centimeter, 2 meter. You have something like, which is of the order of 30 centimeter. When you have such a system, which is some liters of water, typical time for filling the tank is roughly 3 hours. So it's not too long in this case. You have larger tank that takes longer to fill. It can be sometimes 10 hours, but just a question of matter of the fill. To answer this question, a bigger pipe will not change a lot of things, since you will have mixing at the end of the pipe. The problem, for example, in this system was not the pipe, it was the thickness of the tank that was small, which is of the order of 10 centimeters. That was the limiting effect for filling the tank. So we don't want some mixing because the width of the tank was very small. So it just depending on the tank. For example, we had axisymmetric tank, which was quite large, and we had larger pipe in diameter to have a larger flow rate and less velocity and almost no mixing. What we changed is that we had four points where the fluid arriving in the tank, so that helped a lot. So and then you can have a larger flow rate. So this is really dependent on the configuration of the experimental tank you want. Many experiments were done in 2D, and in 2D, since the width of the tank is small, you may induce mixing if you have a too large flow rate because of this finite width. Just for the 4 hours, and this will help for the first question, a typical stratification in the lab. The laboratory. So we have many stratification. I will just show one, which is this one. It was taken, I think this one was in, I don't know, it was one from Baptiste Bourget, who finished his PhD in 2013. It's an example of the stratification we can obtain. So that's so you can see that in experiments, so the experimental experiments is in blue, this one, and the red line is a linear fit of the stratification. So you can see that so it's moved so that we can see the difference between the experiment and the slope. And we have a very, very nice linear stratification almost everywhere in the tank. To answer the first question, the diffusion. So this stratification is very stable, and we don't have any problem of diffusion except in two regions near the surface, where you can see here already that you have some mixing and that the stratification here it's more homogeneous. And usually during time, you have some mixing at the bottom of the tank where it becomes more homogeneous. But in the middle, the stratification stays for a long, long time. And after 5 days, we still have the same stratification with the same linear slope during many days. When we perform experiments, it depends the experiments you want to do. Some experiments, we really wanted a very nice linear stratification. Probably you have seen some internal wave mode this morning by Manican and Mathieu. So you want a stratification that is linear over the whole height. And for this, you need to do experiment just after filling the tank where this region and this region are not homogeneous. In many other experiments, you can do your stratification on one day, you experiment the afternoon, the day after, and the day even after, and you will get very similar results. So diffusion, of course it happens, but it's not really a problem if you have only salt. And typically in the lab, you can have these frequencies, that is in the tank, n is equal to the square root d times the reference density. I think you had you have seen this morning, and it's a characterization of the frequency. And this value you have here, it's a typical value we have in the lab in most of the experiments with 30 centimeters stratification. You go to 1 meter, usually n is a bit smaller, but not so small. It's about 0.75, something like that. And it's what we have in laboratory experiments that has been compared with oceanic measurements. You will see that in another lecture. Okay. So this at the layers of the fluid. Okay, I think you're talking about the movie. Yes, so if I come back here and I go to the end of the movie, I think you're right. That was a movie that was made for presentation. So since you don't want to have a filling that takes 3 hours, you're going fast, and it's a very classical problem. If you go too fast, you have some layering in the stratification. It's what you see in this movie. If you reduce the flow rate, it's what we have in the lab, which is such like this experiment. And in this experiment, you have no layering at all. So that's a question of the fast stratification. A classical also stratification, classical problem is layering. So if you have some layering, this is because you are going too fast, or because the mixed tank is not well mixed. That's another problem you can have in the lab. You can have also a problem if the two pumps are not perfectly accurate. Q1 and Q2 are not related by 1/2 precisely. This layering you can see here, it's clearly due to because the filling was too fast. And when the filling is too fast, you can see this kind of layering here. Experimentally, when you have this, it's a bad sign for your stratification after. In nice stratification, we obtain this is very, very small. And that's why this is typically the stratification we use for laboratory experiments after. If you have very, very small variation for internal waves, it won't matter at all. Okay. So, is there any other question on this part? Oh, yes, I completely forgot to say it. So, thanks for the question. I wanted to. So in this case, when it's for salt, what you do, I think that's the measurement is done using a conductivity probe. So basically, you have your tank, you have the water, and here you have a system. Okay, and that's a conductivity probe. So, and the conductivity probe is sensible to the concentration of salt. Using a calibration, you can relate the concentration of salt to the density. You can do this calibration. Usually, you take care of the problem of temperature, so you rescale everything with the same temperature. So you have access to the density, and then here you have a step motor. So the system is going this way, and if you go very, very slowly, you don't alter the stratification, and you measure the density as a function of z when you're going down. And using the, so you measure the concentration of salt from this conductivity probe, and with the calibration, you obtain the density. And this is how you have this experimentally. That's the new version, a very old version. You can take water at every centimeter inside the tank and measure its density. You have some systems that measure the density very accurately. And so you can take some a piece of water at every centimeter and have the stratification, but it takes a very long time. Here it takes a few minutes to have a very nice stratification in this way. So that's for linear stratification. I will just say a word on the generalization. The generalization, we can adapt this for every any stratification, any tank shape. So what you have to do is you have the desired value of rho T times Z. You know A as a function of Z. With this, you can compute Q1 and Q2. The two flow rates. You can also compute the density Q1, Q2, rho S, rho M naught, V M naught. So you have many solutions to this problem. Just you have some limitation. First, all these quantities need to be positive. So that's the first limitation. And you have also a limitation of the pump for the flow rate you can have the lab, and Q2 has to be small. So getting all this limitation, you have some solution to this problem when you choose the one which is the best for you. And you can have the stratification you want by this generalization of the equation I've shown you before. And this is used in many experiments by that we have used in Lyon, that Samuel Bourri has used during his PhD, and that we have used in the lab, that we're currently using with our PhD students, Corentin Pacari. He has a tank that is not with a constant area. We have this code, and you need to control the flow rate by a computer, but it's not so difficult. Of course, you cannot have a stratification that is varying too fast, and this is because a problem of diffusion. The diffusion doesn't allow to have very fast transition. So that was the first thing with the double Birken method that we use every day in laboratory experiments, and that's how we implement. And that the first things master students, PhD students learned when they arrive in the lab is how to make a nice stratification. When they know that, you have you can do experiments. If you don't know to have a nice stratification, that's something complicated. So that's the first thing you need to learn, is how to make good stratification. I just want to talk about then on a thermal stratification. Is not an easy one to do. It's just a very nice experiment I wanted to discuss. And it's not something we use every day in the lab, but it's a stratification that's made with temperature. And it's an experiment we have started to work with people from geophysicists, some geophysicists in Lyon. And it's called penetrative convection. This has many applications for what happens in the Earth and in some planet, which is transition between convective zone or radiative region in the planet. So to discuss this, I will go back to the beginning of my talk, and I will take this copy it. And it's here. I will just focus on this part. So that we just add that T. the temperature, that's O, and here you have the density of water. And we'll use in this experiment properties of water. Water has a maximum density at 4 degrees. So the density is increasing between 0 and 4. The density is decreasing between 4 and ambient temperature. And this will lead to a very, very interesting system, which is the coupling between convection and internal gravity waves, which you have seen this morning, or with more than internal gravity wave, stable stratification. So this is called penetrative convection. The work I will discuss, so you have different studies in France. You have the study that we have done in Lyon with Stéphane Labrosse, Thierry Alboussière. This is from the laboratory that is Laboratoire de Géologie de Lyon at ENS. And that's a work that we do together with Philippe and myself. And we have, that's a work, we have, there will be some studies next year. There have been some other work in Marseille by Michael Lebars, Patrice Legal, Irfé. And you have also some other works that's in experiments and some numerical simulations also. So the system is the following. So you have a tank. Is this? Basically, the tank is around 20 centimeters, something like that. You have here a system with copper and some fluid that is, you can impose the temperature T equals 0 degree. And you start at T equals 0, you use a system to impose temperature T equals 0 at the bottom of the system. At the top, you have ambient temperature. -25 °C, roughly. And to see what's happened, you have a system with this sum. Every centimeter you have a thermistor. So you have a system to measure the temperature of the system, which is called with a thermistor. When you have this, what happens? So I will show an experimental movie. And this. Is this one. So it was already 7 years ago. So on the right part, you have the signal given by each system. So you have a temperature as the function of the height in the tank. On the left part is just a visualization with a camera and backlight, so you can see what's happening inside the tank. You have some ombroscopy. It's similar to what you have seen before in previous movies. There are some treatments here to see what's happening, and I will come back later in my second lecture probably on how we can have quantitative information just by visualization with the camera and some backlight. And if you do this system, yes. So you start, the system is at t equals 0. So for the now t equals 0. At the beginning, nothing really interesting is happening. And then you have some temperature that is going decreasing because you have a temperature exchange within the fluid. And you can see here there is a transition region. Here you are below 4 degrees in the first centimeter. Then you're here below 4 degrees. And you see that there's a clear difference. Here you can see some motion. So if you have seen many talks on fluid mechanics, these are characteristic of convection walls. So here you have convection. And then here there's nothing, but the temperature is slightly increasing. Yeah. So in this region, you have this convection wall that you can see here. And basically, after some time, so the movie will continue for a long time. We wanted to see what was the evolution of the interface as a function of time. So you can still see the convection. The temperature here is homogeneous. You have some air layer when the temperature is increasing. Then the temperature is at 4 degrees, and it's because the fluid is mixed because of convection. And then here the fluid is slightly increasing, and this is a profile that is determined due to diffusion. And here you have convection, here you have a stratified fluid. And this is what was interesting in this system, is that what was the interaction between the convection and the stratification. So the stratification, you can control it with the temperature, and you had this green line was a theoretical profile. It was not perfect, but we had it was not taking into account some loss, some heat loss on the side. And so it's hard to see, but here you can see some lines that if you look very carefully, you zoom, you can see the propagation of internal waves. And so that was the second question. You have how energy is transferred from the turbulent convection region to the stratified region. And that's a question that is very, very interesting. And we still don't have the complete answers. Can we predict the quantity of energy that is transferred from one region to the other? If we have internal waves, what are the angle of propagation? What is the wavelength? There are many, many questions that are underlying with this region, where you have these two convection, which is unstable stratification, and stable stratification with a stratified, with some stratification, and the how they are coupled is a very, very important question. I just wanted to explain why such study may be interesting. So that's what I will just do a small sketch in this system. So we have here the temperature, and here, so here the temperature is, sorry, Here it's Z. What I observe is temperature T. We are at 4 degrees. You have the system which takes this shape. And here you have a system which is going to 25 degrees C. And here you have unstable stratification, which leads to convection. And that's why you had this convective wall here. And here you have a stable stratification. And here you have some propagation. So here you have the stratified flows. Clearly, you have seen its movie, it's hard to see something in the stratified region, so you don't see a lot of energy. Probably it's because it's very small, so you see convection and you don't have enough signal to clearly measure something. But here you have the propagation of internal gravity waves. And the question is how they are related, they are coupled is a very important question. So coupling between. And still it's an ongoing question, I don't have any answers. This system, convection and stratified flows. You can see in the below it was well mixed because of the convection. In experiments we are doing in Lyon, we add another important parameter, which is rotation. And the rotation will affect the behavior of the stratified flows as well as the convective region, so that we have different features. So, any reason for symmetric two-hole structure part? There is no reason, and I'll just come back in this movie. I have chosen to draw two convective holes. And in fact, in this system was more in 3D, so it's hard to. You can have only a single wall as classical Rayleigh-Bénard convection. This is possible. It clearly depends on the size of the system. In this system we have studied, it was a squared base. So we had the same distance in this direction that in the width. So in fact, you had wall that was not always in the plane. So you see that it's many walls that are moving, and it's because the shape of the area was a square. So a single wall is really when you have small system in thickness, and that's the first mode you have. Here you have many modes. That's why sometimes you can distinguish some walls, but you have multiple walls here, and it's really because of the geometry of the tank. Okay, So that's another way to work with the stratification, is to work with temperature. Here I have chosen a more complicated system because I wanted to present this is a beautiful work, I think. But you can have a nice, easy stratification to do with temperature, and I will show you another example later in these lectures. And okay. And also, I just want to say a word on this system. In Marseille, Michael Lebas has worked a lot in this system, and he has worked to compare numerical results and experiments, and the numerical simulation were possible because of the realization of the experiments to choose the good parameters for the numerical simulation. And it's this work together between experiments and numerical simulation that's what helped a lot of the understanding of the system and will help to understand the generation of internal rate in this system. And it's the case in many, many other systems. Okay. I will just explain now what happens when we have both. It will be a very, very short part, but I think that's something very interesting. You have seen something close, what I will show you yesterday in the first lecture, almost at the beginning. I think you have seen a coffee cup with this double diffusive mechanism. I will show you, with gravity current, which is a system where you have salts and temperature. So I will go to this nice movie. So you have done again a gravity current, which is this one at the top. This one at the top is a warm fluid, so density is smaller. It's slightly salty. So you have salt and at one part you can see that you don't have you have strange features that will appear in the tank that you can see here. You can see some sinking, like some plumes from the top that is going down. It's because you have diffusion and you don't have the same system because you don't cool the system the same way on the side and in the middle. And also it's because the diffusion of salt and the diffusion of temperature is not similar. They have 2 orders of magnitude difference, and which leads to the formation of such behavior, and that may have very, very interesting features in different systems. And this is called because of the fact that salt and temperature does not diffuse at the same time scales because of the diffusion coefficient. And I just wanted to show you this movie. It may happen in the lab that you have sometimes problem because you have modification of the temperature in your system and you work with salty stratified fluid. And if you have both, you may see few strange things happening in your stratification, and it could be due to double diffusion. So that's why I wanted to show you. So that may induce some problem in may induce some problem in your experimental study, in your experimental setup. And it can also lead to very interesting feature. So, and one of them is the staircase stratification. And something you can see in the Arctic Ocean. And staircase stratification, I will just draw a line to explain to you what it means. So you have the altitude Z, you have rho, the density, and you have a system that is going this way. So you have the stratification, you have a layer. You have a system like that. And you can see that in ocean, and it's a system where here you have convection, and in the other system here you have stable stratification. And it may happen because the temperature has diffused at another time than salt, and since the density depends on both the temperature and the salinity, if the temperature changes, you can change the density, and the system that was stable at t equals 0 may become unstable after some time, and it's what happens in such a system. And we had one or twice this kind of features in our lab because of some temperature issue. And it is due to the fact that there is a strong difference in the density, in the diffusivity of salt and temperature. Okay, basically there may of the order of 2 or 3 orders of magnitude. Okay. So, is there any question on this part? Not, I will, okay. So if not, I will just show you the beginning of some movies. This is the stability of a pancake vortex in stable stratified flows and rotating flows. So I will add rotation in the system just for this part. I think that's a nice study. We had made some experiments with someone that I can see online, which is Samuel Bourri. That's I will use some movies made by Michael Lebars in Marseille. So that the stability of the pancake vortex in stable stratified more than stable in a rotating stratified flows. So I will do again injection of fluid. So in the lock exchange experiment, I have done injection of fluid from the top. Now I will, from the side, and I remove slowly a barrier between two fluids. Now I will look at the injection of fluid from the top, and I will see what's happening. So, and one of the goal of this section is to see that stratification and rotation, they have common points and they have also some differences. And here we can see that there is a competition between stratification and rotation in this study. So it's experiments in which stratification and rotation plays a similar role, but they are in competition. I will try to explain I will explain this competition. So that's a very, very good question. So if I come back to this question, the length scale of this, and this clearly depends on many things. It clearly depends on the temperature difference, the salinity, on some time scales of diffusion. It's very hard to answer this question. If I remember the papers I have in mind, I don't remember the scale in the ocean. I think it was some meter scale. In the lab, it was few centimeters. It really matters of the temperature you have and the salinity of the system. And because, in fact, you need to have convection. So clearly it will depend on the salinity of the fluid and its temperature to have a temperature so that it compensates the salt to have a reverse density. The temperature, the diffusion of temperature is the fastest. So clearly it will clearly matters. In fact, you can neglect almost the diffusivity of the salt as compared to the diffusivity of the temperature, and it is the diffusion of temperature that will matter more. Clearly, the time scale will be at play, but it's not the only one, since it clearly depends on the initial stratification, because if you may need a stronger temperature difference to have a point where the density stratification becomes unstable. So it will clearly depend on the initial stratification. And it will affect the length scale of the steps. I don't have a complete answer for this. It's a very complicated question. Yes. It's challenging. It happens when you don't want that it happens. So that sometimes in experiments, you can see things that you don't want. And sometimes you don't want and you don't know how to remove these effects. If you want to do it, if you want to control it, it's not easy. I don't know a lot of works on such topics, and there's a study I want to perform in the future. There have been worked in numerical simulations. There are some work. I know that there's some work by Detlef Lose in 20. Some work in China. I don't remember the name. That's in experiments. There's something that is very interesting to study. It's not easy to implement, to have it controlled in experiments. So that's something that has been still has to be performed. Okay, so if I go back to this study, and I think I will finish my lecture today by showing you 3 movies, a movie of this vortex, and tomorrow I will start with explaining some things about this movie. So I think this is this one. So that's a movie made by Michael Lebars during the PhD of Oriane Aubert, and in collaboration with John Onu from UCLA. That's why you have this PinLab UCLA. So this is the setup I want to study. So you have a system that you can recognize. This system is the system used to make the stratification. That's the double bucket system. And you fill the tank this way. You put the system on a record player, and this is a way you have rotation. We have made also similar movies in Lyon. This one has this a nice figure, and you have injection of what is called a plume. You will see that in a minute. You still have the buoyancy frequency or the varicella frequency that controls the stratification, and you will play with the rotation. Okay. And you add some dye to have some contrast, like from the gravity current to see the difference. So the plume, you inject some fluid, and you look at the behavior of the fluid in the system. So in this first movie, you can see that the first case is non-rotating homogeneous fluid. You can see that it's going. Sorry. It's going below. It's going to the bottom, and it will form a gravity current, slightly denser. It's from a gravity current at the bottom. Now the second case you will see is you have a rotating system. So you can see that it's rotating, and what you have, you can see that you have fluids everywhere, and you form a vortex that is anticyclonic, so it's going, it's rotating in the other direction as the system, and you have a column. In fact, it means it's because Coriolis force restores horizontal motion, and I will show that in the next lecture. When you have a rotating stratified fluid, you form flat layers. It's similar to gravity current that we have seen before. No vortex, and you have different layers because it's because of the injection, but it's more horizontal, and because stratification restore vertical motion. You have seen that this morning with mechanical material, and I will start with that tomorrow. And if we have both, you have this very, very nice pancake vortex with this nice, very nice shape, and you have both stratification and rotation. which is very, very stable in time. And it's because you have restoring force in the vertical from the stratification. You have restoring force in the horizontal because of rotation. And you can have a system where you have, you can calculate the vortex height compared to its diameter when you reach 1/3. And this is something I want to explain a bit more during my second lecture on how we can have this system. And I think this is the movie I wanted to show you. I will not start the derivation of this system today. I just want to say that these pancake vortex are very visible in oceanography. So here it's in Atlantic Ocean. This is Spain. This is Africa. Here you have Gibraltar. And you can see these patches here. You can see in salinity, in temperature, that you can see here, that are called MEDIs. MEDIs from Mediterranean Sea, that is going to the Atlantic Ocean, and that evolve and are stable for a long time. And if you look with the depths, you have this shape in salinity and temperature, which looks like the pancake vortices that you had in the lab. And that's why we wanted to understand why such systems are stable, and I will try to explain looking at this experiment. The system is slightly denser. More precisely, the density of the injected field, I'm waiting for the last movie, so is density in between the stratification. So yes, in this one. So basically the density of the injected fluid is smaller than the density here. That's why the fluid goes up, but it's larger than the density here. That's why it forms some layers. It will normally choose the layers at which corresponding at its own density. You have multi-layer because you have some mixing during the injection. So that's why you have layer here, here, and here. The density corresponds to the density of the ambient fluid at this side. And it's same case here. It will correspond to the density near the density of the ambient fluid here corresponds to the density of the fluid inside. Okay. So tomorrow, I think I will end up my lecture today with this movie. And tomorrow we'll start here on going back to stratified flows to explain why this pancake is stable, and start with internal gravity waves after. If you have any question, don't hesitate to ask this question on the chat. Or if there are any questions on YouTube. So if there is no question, I will thank you for listening to my lecture, and I will see, I think, I will see you tomorrow.
Thank you, Silva. Thank you. It's a very nice talk.
Thanks.
So we'll resume tomorrow at 1:30 India time.
Okay.
Professor Thierry Duxo would talk about nonlinear internal waves. and the continuation of today's lecture would occur at the same time.
Yes.
So thank you everyone for joining in. See you tomorrow.
Thank you. See you tomorrow.
Bye-bye.